hello everyone. So we already discussed Biot-Savart expressions in the last session, right? So in this session, we are going to apply Biot-Savart law to derive the expression for magnetic field due to a long straight current carrying conductor and also the magnetic field on the axis of a circular current carrying loop. These are the two applications of Biot-Savart law. So in these sessions, we are going to discuss the first one, magnetic field due to a long straight current carrying conductor. Our first application is magnetic field due to a straight current carrying conductor. See, here we are having a current carrying conductor, infinitely long straight current carrying conductor. We can name it as XY. Okay, so we need to find the magnetic field at a point P perpendicular from the conductor. So this here, if I am giving O, then OP will be equal to A. Here OP is equal to A. Okay, so here I am considering a small elemental area. Okay, this is DL here. So this is DL vector and the position vector from this point to P. This will be R. Okay, so the angle between the vector DL and vector R is theta. Okay, so here we need to apply Biot-Savart law, right? So according to Biot-Savart law, magnitude of the field dB, here the magnitude of the field dB due to a current carrying element dl, we need to find that. So how we can write that? dB will be equal to mu 0 by 4 pi I dl sin theta divided by r square, right? This is our Biot-Savart law. Okay, so again I am explaining the figure here. See, from this point to here, the midpoint, the length is L. Okay, here we are taking the angles also. It is phi 2 if we are taking from the infinity to this point, and this is phi 1 from this point to this. Okay, so we are considering a right angle triangle here. See, OP, this if I am giving Q means OPQ. So from the triangle OPQ, what is theta plus phi? Theta is this and this angle is phi. So what is theta plus phi? This will give 90 degree. Okay, so what is phi here? Phi is equal to, or what is theta here? Theta is equal to 90 minus phi. So therefore we can write this as sine theta. In this equation, sine theta we can write as what? Sine 90 minus phi, which will give cos phi, right? So from this triangle, what is cos phi? What is cos phi? See, cos phi is this one, right? So this is the adjacent side and this is the hypotenuse. So that will be A by R, adjacent side by hypotenuse. Or we can write R will be equal to A by cos phi, right? R is equal to A by cos phi. What is 1 by cos phi? Which is equal to A sec phi. So we can write this as A sec phi. Again, we need to find tan phi. From this, we need to find tan phi. That will be, tan means opposite side by adjacent side. So what will be here? What we will get here? L by A. This is L, right? So L by A. This is opposite side by, and this is adjacent side. Opposite side by adjacent side will give L by A. So what is L here? L equal to A tan phi. Okay, so we got L is equal to A tan phi. If I am differentiating this, what we will get? DL will be equal to A is constant there, right? What is differential of tan phi? That will be sec square phi, then d phi. Sec square phi d phi. We will get sec square phi d phi. So instead of this dl, we need to put a c square d phi. So our equation will become, what is our equation? dB is equal to mu 0 by 4 pi idl sin theta by r square. So this equation will become dB is equal to mu 0 by 4 pi I into I dl. What is dl? A sec square phi d phi into, instead of sin theta we have cos phi, right? Cos phi. So again we can write this as dB will be equal to mu 0 by 4 pi into I into, here we have r square also. What is r there? A square sec square phi. So this will be sec square phi and sec square phi will go. So what we will get here? I into cos phi d phi. So I into cos phi d phi will get here. So dB is equal to mu 0 by 4 pi I cos phi d phi. Okay. So see, next we need to know the direction of the magnetic field. See, if I am taking this point, okay, the current is in this direction. If I am taking our right hand thumb rule, so then the point is here. So if I am holding my right hand in this, if I am gripping the conductor in my right hand like this, then the extended thumb will give the direction of the current and the curled finger will give the direction of the magnetic field. So my point is here means this curled finger is in this direction. So this is towards the paper. So inward the paper, right? So here for this point magnetic field is inside, right, towards the plane of the paper. So if I am considering here also, if I am considering one here, then this also will give the same direction. Magnetic field will be in the same direction in all cases. If we are considering any number of such elements, the magnetic field will be in the same direction. So how we can find the magnetic field for the entire conductor? Entire infinitely long straight conductor. How we can find this? So for that we need to integrate this. So how we can integrate this? Total magnetic field will be B. Okay, we give integral dB minus phi 1 to phi 2 we need to integrate. Okay, so our equation is minus phi 1 to phi 2 mu 0 by 4 pi I cos phi d phi will give, right? So this will be mu 0 I by 4 pi integral minus phi 1 to phi 2 cos phi d phi. What is integral cos phi d phi? It is sin phi. So this will be mu 0 I by 4 pi sin phi 2 to minus phi 1. So by solving this, what we will get? Mu 0 I by 4 pi sin phi 1 plus sin phi 2. Okay, so this is the total magnetic field here. Okay. So here we have some special cases. A conductor, first case is a conductor infinitely long and point P lies near the middle of the conductor. See, like this. Infinitely long conductor and the P is in the middle of the conductor. Okay, so what will happen here? Here our phi 1 and phi 2 both are 90 degree. Phi 1 and phi 2 will be 90 degree. So what will be the answer? What is our equation? Mu 0 I by 4 pi A into sine 90 plus sine 90 degree. So this will be mu 0 I by 4 pi A into, this will be 1 plus 1. What is 1 plus 1? It is 2. So our D is mu 0 I by 2 pi A. Okay, that is mu 0 I by 2 pi A will be the magnetic field then. Next is point P lies either side X or Y. Either X or Y. That is for semi-infinite length. For semi-infinite length. Semi-infinite length. See, like this. If I'm taking this as an X and Y, then P is either X or Y. Okay, so here theta 1 will be 90 degree and theta 2, sorry, phi 1 will be 90 degree, phi 2 will be 0 degree, right? So the equation will become sine 90 plus sine 0 will come. So B will become mu 0 I by 4 pi A only. So for this case, we got B is equal to mu 0 I by 4 pi A only. Point P lies on axial position. See, this is our XY. So I'm considering an axial position here. So in this case, the magnetic field will be 0. So these are the three cases we need to consider. Okay. Hope you understood thoroughly about the how to find the magnetic field in a straight current carrying conductor. So we can go with a numerical. Okay. See here, following figure shows two current carrying wires 1 and 2. Find the magnitude and direction of the of the magnetic field at points P, Q, and R. So we need to find the magnetic field at point P, Q, and R. Okay. For first case we can take, see here the conductor 1 is, this is conductor 1 and this is conductor 2. The current carrying conductor 1 is given, the current is 20 ampere and here the current is 30 ampere. Okay, the direction of current is in this direction and this is below direction, right? These two are separated by a distance of 20 centimeter. Okay, so if you are taking this, according to right hand grip rule, the field B1 of wire 1, okay, here field B2 will be there. So here B1 is the magnetic field of this current 1 and B2 is the magnetic field of B2. So according to right hand grip rule, if you are considering this point P is in the left side. So if current is in this direction, right? So how the direction of this? So magnetic field will go in this direction. So this point will be outward. So here we will get an outward condition. Okay, the magnetic field will be in outward. Okay, so we can write magnetic field at P will be equal to B1 minus B2. Okay, so here this B1 will be inward, and here according to this, here we will get inward magnetic field, right? So this will be outward and this will be inward magnetic field, right? So here we will get, this is mu 0 I1 by 2 pi A1, right? Minus mu 0 I2 divided by 2 pi A2. Here we will get 4 pi into 10 raised to minus 7 divided by 2 pi into 20 divided by 0.10 minus 30 divided by 0.30. How this 20 and 30 came? See, here we will have I1 and I2. I1 is 20, I2 is 30, right? Then here A1 and A2 is there. That is the distance from the point to this point, this conductor, right? Here for B1, if you are taking this will be from this middle point, this will be from here to here, this is 10 centimeter, right? That is here, A1 is 10 centimeter. See, from here to this point, from here to Q it is 10, Q to this conductor 10, this is 10. So total 30 will come. So we got 0.30, right? So the answer will be 2 into 10 raised to minus 5 Tesla. So the direction of this will be normally inward. Direction will be normally inward. Okay. So again we need to find at Q. We need to find at Q. So here both B1 and B2 point normally inward. Okay, so both will B1 and B2. So here we will take B1 plus B2. So both will be inward. Okay, so here we are taking this as BQ will be B1 plus B2. So here we will get the same equation. We will get 4 pi into 10 raised to minus 7 divided by 2 pi into, here again current will be 20 divided by, what is the distance here? It is 10 centimeter. So 0.10 plus 30 divided by, this also will be 10.10. So here we will get 10 raised to minus 4 Tesla, and the direction is normally inward. Direction is normally inward. Okay. So again we need to find at R. So how we can find at R? Here at R, B1 will be inward and B2 will be outward. Why? It's because current is in this direction, in the downward direction. Current is downward direction. So if you are taking like this will come this way. So this will be inward and this will be outward direction. So here we will get B1 inward, B2 outward. So again at BR, B2 minus B1 will come. Okay, so this will be 4 pi into 10 raised to minus 7 divided by 2 pi divided by, here the current will be B2 minus B1. So 30 minus 30 divided by 0.10 minus 20 upon 0.30 will come. Okay, so this will give 4.5 into 10 to minus 5 Tesla and pointing normally outward. At R, it will be pointing normally outward. Okay, so this is the problem. So this you can do as a homework. The same method you can do here. Next problem. Two infinitely long insulated wires are kept perpendicular to each other. They carry currents I1 is equal to 2 ampere and I2 is equal to 1.5 ampere. So here I1 is 2 ampere and I2 is 1.5 ampere. Find the magnitude and direction of the magnetic field at P. At P we need to find the direction and magnetic field. Okay, if the direction of current is reversed in one wire, what would be the magnitude of the magnetic field be? So we need to find both these. So how we can find? We have two infinitely long insulated wires are kept perpendicular here. So these two kept perpendicular. So what will be B1? Which will be mu 0 I1 by 2 pi A1, right? So this will be 4 pi into 10 raised to minus 7 divided by 2 pi into 4 into, this is 4 centimeters. So 4 into 10 raised to minus 2, right? Into what is I1 here? In this I1 is 2 ampere. So here we will get 10 raised to minus 5 Tesla, and the direction of this is into the plane. Okay, into the plane. Then again, what is B2? Mu 0 I2 by 2 pi A2. So which will be 4 pi into 10 raised to minus 7 into 1.5 divided by 2 into what is 3 centimeter, right? 2 pi into 3 into 10 raised to minus 2. This also will give 10 raised to minus 5 Tesla. Okay, so what is B? Total magnetic field will be B1 plus B2. So this will be 10 raised to minus 5 plus 10 raised to minus 5 will come, which is equal to 2 into 10 raised to minus 5 Tesla, and the direction is into the plane of the paper. Okay, so the magnetic field will be, total magnetic field will be 2 into 10 raised to minus 5 into the plane of the paper. And the next question is, if the direction of current is reversed, if the direction of anyone is reversed means, then magnetic field will be 0 there. Any one of the direction or any one of the field is changing means magnetic field will be 0. So here magnetic field is B will be 0. Okay, so this is the problem. Hope all of you understood the concepts and you are able to do the numericals. Okay, whatever the numericals are coming, you are able to do. So please do the homework also. Then you can do more and more problems, numericals with these concepts. So next class we can discuss the magnetic field, the next application, magnetic field due to a current carrying loop. Okay, thank you.